All right, so chapter 11 is going to be our intro to organic chemistry. And just as a sort of a preview, the second half of the semester is going to be very different than the first half. Organic chemistry and biochemistry tends to be more of a visual look at chemistry. There's virtually zero calculations involved. It's all about the structures and the reactions that these compounds are going to undergo, together with how we apply organic chemistry to the behavior of biomolecules, so things like proteins and carbohydrates and lipids, etc. So let's jump right in and talk about what organic chemistry is. So in contrast to the first half of the semester where we were doing general chemistry, organic chemistry, we're going to be focusing mostly on the study of carbon and carbon-containing compounds. Right, so this is really going to be the central theme of organic chemistry. We're going to look at carbon and how we find it in these different types of compounds, and some of the properties and both physical and chemical of our organic compounds. So what is an organic compound to begin with? Well, it's made up mainly of carbon and hydrogen atoms. So carbon and hydrogen, and then we're also going to see other types of non-metals in there as well. So we may see things like oxygen, we may see nitrogen, we may see sulfur, we may see some phosphorus, and then possibly some halogens as well. All right, so typically for organic chemistry, the study of organic compounds, we're looking mostly at non-metals. All right, remember the types of bonds that hold nonmetals together are your covalent bonds. Organic compounds are typically found in common products. So for instance, you have a bunch of organic compounds in things like your gasoline, right, in your bread, for instance, made up of organic compounds. And you can think of many examples of organic compounds. Typically, when we write the formulas for our organic compounds, we usually write the carbon first, the hydrogen second, and then any other elements listed after. So for instance, we can say glucose, which is an example of a sugar, has the chemical formula C6H12. O6, right? This is an organic compound. There's carbon, there's hydrogen in it, and then there's also oxygen. Similarly, something like sucrose, which is just the technical name for table sugar, right? It belongs to the same family as glucose. It has the chemical formula C12H22. 11. Right, so that's going to be the general way that we're going to write the formulas for our organic compounds. What are some of the characteristics of our organic compounds? Well, we mentioned that because they're typically made up of non-metals, we would predict that the type of bonding involved would be covalent bonding. Between the atoms. In terms of the melting points and boiling points, these tend to be low. For the melting point and the boiling point. These organic compounds tend to undergo combustion. They tend to be flammable. And they undergo combustion reactions readily. Right, remember, combustion from chapter 7. So recall, combustion is the reaction with oxygen, and typically we produce carbon dioxide and water vapor as the products, right? And organic compounds are really good at undergoing combustion reactions. Your organic compounds, in terms of their solubility in water, they tend to be insoluble. In water, and because now our organic compounds are insoluble in water, what that means then, because water is polar, or since water, we know that water is polar, if your organic compounds don't dissolve in it, then your organic compound or molecule are going to tend to be non-polar. Right, these are some general trends. There are always exceptions, but we're just looking generally at some of the characteristics. In contrast to inorganic compounds, right? So organic compounds typically held together by covalent bonds. Your inorganic ones held together by ionic bonds. Melting points and boiling points tend to be high. Solubility in water, these tend to be soluble. And then in terms of the types of bonds, well, we already mentioned ionic bonds mostly. Burning in air as compared to your to your organic compounds, your inorganic ones do not readily burn. Right, and we have here a couple comparisons. So this is propane here on the left, that's an organic compound, and then in contrast to it on the right side there, that's sodium chloride, regular old table salt. This is inorganic. And your propane here, which is C3H8, it's propane, and that's an organic compound. All right, so just to recap some of the most important differences. So we have here our organic on the left side, and then we have our inorganic compounds here on the right. And the examples that we're comparing again here are propane for organic compound, and then we have table salt or sodium chloride for the inorganic. All right, so this is a really good table that summarizes some of the differences between organic and inorganic compounds. All right, so let's take a quick look here at some of the characteristics. So it has a high melting point. We would predict that to be inorganic, not soluble in water, or non-polar, that would be organic. Has the formula carbons and H's. Would predict that to be organic. Has the formula MgCl2. There's a metal in it, so right away we can think inorganic. Right, there's no carbon in it. Burns easily in air. That tends to be your organic compounds. And covalent bonds, we typically find those in our organic compounds as well. All right, so we're now going to take a look at one of the simplest types of organic compounds, and these are known as hydrocarbons. And the name hydrocarbons actually tell you the types of atoms that they contain. So hydro here would mean they contain hydrogen, And then obviously carbon would mean that they contain carbon as well, right? So hydrocarbons are organic compounds that contain hydrogens and carbons in them. So one very important thing to keep in mind when we start looking at our organic compounds, whenever you have carbon and you have to draw the structure for an organic compound, you want to make sure that every single carbon has 4 bonds attached to it. Right, and we saw this when we did our Lewis structures. These 4 bonds that carbon can form can be 4 single bonds. It can be 2 double bonds. It can be 1 double and 2 singles. Or it can be a triple and 1 single bond, right? So any combination of those would satisfy the fact that your carbon likes to form 4 bonds. The other thing that we want to make sure that you don't violate here is that hydrogen can only form 1. All right, and your hydrocarbons are going to contain hydrogens and carbons. All right, so some examples here of hydrocarbons. So CH4, methane, we've seen this several times already in class. Looks like that. So carbon with 4 single bonds. C2H4, which is a compound called ethene. Looks like this. So here each of these carbons again has 4 bonds, but now there's a double and 2 single. And then the last one here is C2H2. This is a compound called ethane. It looks like that. Each carbon again also has 4 bonds. In this case, the carbon has a triple and a single bond. So we're going to take a look at these types of hydrocarbons here in a little bit. So the first one we're going to take a look at is something called a saturated hydrocarbon. And what that means when we have a saturated hydrocarbon, again, we have carbons and hydrogens in it. Saturated means that there are only carbon to carbon and carbon to hydrogen single bonds. In other words, you can think of it as the carbon being saturated with as many H's, hydrogens, as possible. Right, and what that means in terms of the structure is we're just going to see carbon-carbon single bonds and carbon-hydrogen single bonds as well, right? So those are saturated hydrocarbons. There's another term that we give to these. These are also called alkanes, and we'll see this term again here in a second. So let's take a look now at how we represent our organic compounds and our hydrocarbons to be more specific. So we have here one of the simplest hydrocarbon, which is methane, has the formula CH4, right? And again, we've seen that molecule several times. So there are several ways that we can depict the shape of methane. The first one here, this is called a space filling model, and this really would represent what the molecule would look like if you were to zoom in and look at an individual methane molecule. The one right next to it is called a ball and stick model, and this is actually what you made in the lab when you were building your models. And as you can see, right, the shape here of CH4 is that tetrahedral shape. And the way that we draw it to represent that three-dimensional nature is this wedge dash model. Remember the wedge here. That's not the wedge is the one in front. This one. That means the bond is coming towards you. The dash line or the dash bond means it's going away from you. We have our Lewis structure over here. And when we show all of the bonds attached to each atom, we call that the expanded structural formula. And then if we just combine all the atoms together, we end up with the condensed structural formula there on the right. All right, so these are all different ways that we are going to see the structures for our organic compounds. If we start making them a little bit bigger, we can see that the molecule then is going to contain more bonds. So here's another compound called ethane, which has the molecular formula C2H6. There's our space filling model. If you were to build this in the lab using your model kit, it would look like that. And then if you were to draw it, right, using the wedge dash or the Lewis structure, it would look like either of these. Right, so this one here, and that I'm pointing to in green, this is the expanded structural formula. Right, and that gives you really the most amount of information. It tells you what atoms are there, all the bonds involved, and how they are all connected to each other. The one on the right here is just simply taking the expanded structural formula and sort of condensing it. So for example, in our expanded structural formula, we have a C and 3 H's, and then that's connected to a C and 3 H's on the right. Right, so the way that we represent that would be a CH3. That's the one in blue, and then that's connected to a CH3 on the right side. That's the one in orange, right? And they're connected by that bond in the middle between both of the H's, which is that black bond that you show there. So that is how we can convert that expanded structural formula into the condensed structural formula. Notice that when you write the condensed structural formula, it kind of looks like here that the hydrogen is connected to a carbon, right? But keep in mind that the carbons have to be connected to each other, right? Even though we write it like that, because hydrogen can only form one bond. All right, so here's another hydrocarbon, saturated hydrocarbon called butane, which is something that you may be familiar with. Has a formula C4H10, and this is the expanded structural formula. Shows all the atoms and all the bonds involved. It says to predict the shape around each carbon atom. So we look. This carbon has how many electron groups around it? Well, it's got 4 electron groups, right? Each single bond counts as an electron group, and all of those are attached to atoms. So that shape then would be tetrahedral. And that's actually the shape around each of these carbons in butane, right? Each of those carbons has 4 electron groups around it connected to atoms. We can take that expanded structural formula and we can condense it now. So here we have a CH3 that's connected to a C and 2 H's. That's connected to another C and 2 H's. And then that's connected to a C and 3 H's. All right, so this one in red here, this will be the condensed structural formula. And we'll take a look at some of these depictions of the molecules in the next section. So let's just finish up this section, this subsection here, talking about why we want to focus on carbon, and why, for instance, is it that life on planet Earth actually has evolved to be a carbon-based life form. Well, it has to do with the ability of carbon to actually form bigger and bigger things, right? Carbon is good at forming bigger structures, right? We are all carbon-based life forms. Carbon is sort of the backbone of everything in us and around us. And that has to do with the ability of carbon to form chains, right? So carbon can be linked to itself many times, I should say, linked to other carbon atoms, many other carbon atoms, to form massive structures, right? And massive here is a relative term. So they can form chains, just like if you have a normal chain, you're just linking one chain link to another one. Carbon can do that very easily. The other characteristic of carbon that makes it so common and so useful and so prevalent is the fact that it can form rings, right? So if you think of a chain which has two ends to it, and you just attach those two ends of the chain together, you end up with a ring or a cycle form. So carbon can easily form ring or cyclic structures. And as we'll see down the road, those ring structures or cyclic structures are extremely important when it comes to our biological molecules, things like your sugars or your carbohydrates, and then also your genes, your DNA, your RNA, all of your nucleic acids. So in the next couple sections, we're going to take a look at some of the subcategories of these organic compounds.